So welcome to my talk, and thank you for being here. So my talk about hijacking Zen virtual machine for fun and profit. And actually, the technique I introduced to hijack virtual machine work with almost all kind of virtual machine. So actually, it doesn't only work on Zen. So that's why I put Zen in open and closed market. So my name is Nguyễn Anh Quỳnh, and you can call me Quỳnh here. So, okay, here's the motivation behind my talk. So usually, virtualization promise better security for the people who own the virtual machine, because usually you might think that you are safe inside your virtual machine because the other guys on other virtual machine cannot interfere with your virtual machine. So actually, that is not true, because the real power stays in the side, on the hand of people who own the physical machine. So in my talk, you can see that what can we do with good or bad intention if we have the control of the host virtual machine. So in this talk, we explore some technique to dynamically inject code into running virtual machine to hijack its execution. And after that, we can inspect and capture sensitive data. So in this talk, I focus on Zen, but it works with other kind of virtual machine as well. So this technique can be done quietly and secretly without awareness of the virtual machine owner. And it requires absolutely no modification to hijack virtual machine or the underlying hypervisor. And everything is implemented in user space, so it's very easy. And it works with all kind of operating system, be it Linux, BSD, OS, or Windows, or anything. Okay, so here's my agenda. So at first, I introduce something about Zen virtual machine and Zen debugging technique. And after that, I introduce the hijack virtual machine, Zen virtual machine technique. And because the technique can make the system a bit slower, so we might have some performance, so you can see how much it's slow. And in the talk, I have some demos. And if I have some time left, I will discuss how to detect and anti-detect the hijacking technique. Okay, first part. So I suppose that people here, everybody heard about Zen. So yeah, Zen is kind of virtual machine, and it allows us to run multiple virtual machines on the same physical machine. So as in this picture, you can see that on top of the hardware, we have a thin layer of software named Zen Virtual Machine Monitor, or we also call it hypervisor, Zen hypervisor. And on top of the hypervisor, we have multiple virtual machines running at the same time. So in Zen terminology, we call virtual machine domain. So we have 4 domains running here in this picture. And Zen classify domain to 2 types domain. The first one is domain 0, the left one here. And the other type, user domain or domain U. And remember that domain 0 is kind of special privileged domain, and from domain 0 we control all the other domains. For example, you can from domain 0 you can start as a domain, stop as a domain, pause, resume, do anything else. And maybe you already know that Zen is already in Linux kernel, and in the current version you can run Zen from Linux. So I think in the future it will be very widely spread. Okay, something about debugging on Intel. I think this one is familiar to everybody here. So on Intel, they provide some facility for debugging. The first one, you can single step your program by your debugging tool. For example, after single step means after each instruction, your debug program is paused. So your debugger can come to inspect your program. And you can turn on the single step mode by turn on the TF flag in eFlag register on Intel. And when the after each step, after each instruction, the interrupt one is triggered. The other facilities is interruptory. And basically, when the program hits the CC instruction, which is a breakpoint instruction, the interrupt tree is triggered, and it will notify the debugger to come to inspect the program. So yeah, Intel has 2 interrupt for debugging. Okay, so here's how debug is handling in Zen. On the first case, when a breakpoint, the CC instruction is hit in Zen, one exception is raised. And we switch from the virtual machine down to the hypervisor, to the Zen layer. And the hypervisor will check to see if the virtual machine which hit the CC is in user mode or not. In case the virtual machine is in user mode, it return control back to the virtual machine and let it run normally. But in case the virtual machine is in kernel mode, then we pause that virtual machine for debugger, for example, for ZDB, come to inspect. And that's how Zen handles the interrupt tree. And the interrupt one is handled in a similar way. Okay, the next part. So how to hijack Zen virtual machine. So here's my assumption. Somehow we have the control but domain 0. You can be a real owner of the virtual machine, so we have control of domain 0. Or you are the attacker, somehow you break in the virtual machine and take over compromise domain 0 and you have control of domain 0. But anyway, we have the control of domain 0. That's the assumption. So what can we do? We own the other virtual machine. So we control this one. And what can we do with the other virtual machine running on the same physical machine here? So in my talk, I show you that we can hijack the other virtual machine as a domain U. And you can do it silently and quietly. And after that, we can extract sensitive data from hijacked virtual machine. Okay, so here's the first demo for your pleasure. So in this demo, I will hijack the virtual machine and capture on the asset username password. So here's the demo. So I'm running Zen on my machine now, and actually we are in domain 0 now. So let's see which virtual machine is running now. So you can see that we have 2 virtual machines. Domain 0 and the other virtual machine is named Edgy. So now from domain 0, I will run a program. And this program will inject only 1 byte into Edgy. Edgy is a Linux virtual machine. And inside Edgy, we have a secure shell service. Okay, so we try to connect to Edgy here now. Secure shell to Edgy. Enter my username. Actually, my username is Queen here. So now I enter my password. Okay, I'm in. So inside Edgy, you have secure shell service running. Okay. So now, okay, quit. Now inside domain 0, I run 1 program, and this program inject 1 byte, only 1 byte, into Edgy. And you can see, we can do something very cool here. So watch the left window, the domain 0 window. Now I try to connect to Edgy. Can you see? Immediately I capture the username. Enter password. Okay, that's a easy password. Let's try again. This time I connect with another ID, DeepSec. DeepSec. Okay, DeepSec is trying to connect. You see it? Password. Yeah, again, very easy password. Okay, so that means.
But you have to run this code from out of the domain from the exam.
Sorry?
You have to run this code from out of one of the domains of the exam.
I run the program in domain 0, and I capture all the username password inside the user domain.
You have to have control of domain 0.
Yeah, that's my assumption in the last line. Yeah, here's my assumption. I have control of domain 0. So how to do that? Here's my offer. If anybody here can tell me how the last demo worked, I can buy you a beer. Okay, now I explain something about how the technique works. So here we try to hijack a virtual machine. And to do that, actually I try to employ the Zen debugging infrastructure to hijack the virtual machine execution. And to do that, actually what I did is I inject a breakpoint, a survival breakpoint into a running virtual machine. And together with the breakpoint, I have a function. So we have a couple, breakpoint function, and I call it a probe. So I try to inject a probe, which consists of one breakpoint and one function. And the function is also called probe handler. So here's the technique. So I inject a probe into the kernel space of the virtual machine. And together with the breakpoint, you have a probe handler running in domain 0. And whenever the breakpoint is hit here, the switch, as I explained in the last few slides, we switch back to the Zen hypervisor, and Zen hypervisor will notify our probe handler inside the user space domain 0. And here we will run the probe handler, which is a function, and this probe handler will connect access to the user domain here and extract the information out. And that's how it works. Very simple. Okay, yeah, that's how it works. We inject breakpoint into the right place inside the virtual machine, and with each breakpoint, you have a probe handler, and the probe handler will be executed when the breakpoint happens. Okay, so there's some implementation issue in the technique. It's not that trivial. So first one, where to inject breakpoint? Because inside the kernel space, there are many places you can inject breakpoint, but the question is where to inject breakpoint. So you can do it by, there are three ways to do that. At first, you can look into the kernel source code in case the OS has kernel source code like Linux, for example. So if you compile the Linux kernel with debugging information, you can extract many information from the kernel binary. For example, you can know that the virtual address corresponds to this particular line of this particular file in the kernel source code. You can have a lot of information like that. And of course, another way, you can also reverse the kernel binary, and you can check the assembly code to know where to put the breakpoint. And the other way, easy. You can look at the kernel symbol file, which comes with the kernel binary. And in Linux case, that is a system.map file. Okay, that's how to inject breakpoint. The other problem, when you inject the survival breakpoint, which is a CC instruction, into the virtual machine memory, of course you override some instruction, right? CC is 1 byte. So by injecting that byte into the virtual machine, you override one instruction. So of course you have to somehow save that instruction and execute it later after we hand the breakpoint. So there are two ways to hand the breakpoint event. And I propose here two schemes. The first one is inline scheme, and the second one is outline scheme. What is inline scheme? It's very simple. I call it inline scheme because I execute the instruction. I call it the original instruction, which is overwritten by CC in the original place. So inline scheme executes the original instruction in the original place. So here's how it works. In the preparation step, we just suppose that we override the CC into this instruction. So in the preparation step, we copy this byte to another buffer, which I call inline buffer. And then I write CC here. So when the virtual machine executes and it hits this breakpoint here, it will, as I explained in the last few slides, it will we switch down to the hypervisor, and we call the probe handler inside the domain 0 user space. Okay? But because this one is a breakpoint, so the virtual machine is paused. Then we pause that virtual machine, and we stop here, right? EIP will be here. So at this step, we restore the byte we say here into here. And we resume the virtual machine, which is paused at that time. But before we resume the virtual machine, we turn on the single step mode of this virtual machine. So after that, we move back the EIP to here and resume the virtual machine. Okay? But because this virtual machine is in single step mode, so after this instruction, it will trigger the interrupt on. Okay? And we switch back to the domain 0 again. And here, after this, in this step, we will override again CC into here. And we let the virtual machine run normally. So, inline scheme allows us to run the original instruction in the original place. And remember that we need single step mode in this step. Okay, that's how inline scheme works. So basically, it says the original byte, which is overwritten by the breakpoint, and we override the breakpoint instruction with the, when hand the breakpoint event, we restore the original byte, and we move the EIP back and turn on the single step mode. And when you hand the single step event, we recover the breakpoint and disable the single step mode and resume the virtual machine. Okay, the other scheme is called outline scheme. And the outline scheme is different from the inline scheme in that it runs the original instruction in another place, not in the original place. So here's how it works. In the preparation step, we copy the instruction that we will override CC here into a buffer, and we call this one outline execution buffer. And we copy the instruction here, and this buffer must be big enough to contain one more jump instruction, and jump will be set up so it jump back to the next instruction here. Okay, so after that we write CC to here, and we resume the virtual machine. But when this breakpoint is hit, again we switch to the hypervisor and call the probe handler here. And at this step, we move the EIP, which should be here, right? EIP should be here. Now we move EIP back, move EIP point to here, to this buffer, to outline execution buffer. And because the outline buffer contains the original instruction and a jump instruction, so we can execute the original instruction and jump back to here. And the virtual machine works normally. So basically, this idea allows us to run the original instruction in another buffer, not in the original place. Okay, so here's how it works. In preparation step, we copy the original instruction to an outline buffer, and outline buffer contains one jump instruction. So when we hand the breakpoint, we point the IP to the outline buffer. And because the outline buffer contains the original instruction and the jump instruction, so it will execute the original instruction and also the next instruction, and the virtual machine can function normally. Okay, here's one question. In the outline scheme, we need a buffer, right? To keep the original instruction and the jump instruction. So the question is, where is the buffer? Where to get the buffer? And remember that the buffer must stay inside the hijack virtual machine. So where to get the buffer? So we show this problem in the easiest way. So in our solution, we pre-allocate the outline buffer inside the hijack virtual machine. And we first of all, we do that first of all by injecting one kernel module inside the here's a Linux. I insert one kernel module inside the kernel memory inside the virtual machine kernel, and this module will allocate a memory first of all 4 kilobyte, and after that it split this memory 4 kilobyte into multiple slots, and each slot size of each slot is about 20 byte, only 20 byte. So 4 kilobyte is split into multiple slots, and each slot will be allocated for one breakpoint. So you can imagine that with 4 kilobyte you can allocate a lot of breakpoint, a lot of probe. Okay, so our solution is that we allocate the buffer ourselves and split it, and each slot will be allocated for one probe. Okay, let's compare inline scheme and outline scheme. Okay, inline scheme is good because as you see, inline scheme doesn't need we don't need to insert the kernel module inside the virtual machine to allocate the buffer. Inline scheme doesn't need buffer. So that means it doesn't need any cooperation from the hijack virtual machine. It's good. Just inject breakpoint and it works. So it's easy and flexible to deploy. But it's bad. First bad thing is that, as you can see in the diagram here, yeah, here's inline scheme. At this step, we don't have breakpoint, right? In this step, we have breakpoint. This step, we have breakpoint. But this step, we don't have breakpoint. So, in case the virtual machine is multiple, it's kind of virtual machine is SMP kernel, SMP machine, or it support preemptive kernel. So, the other kernel thread can hit this instruction at this time, and that means we miss the breakpoint, right? So, because in this scheme, at one time we don't have breakpoint, so we can miss that event. So that's a bad thing about inline scheme. The other bad thing is that it's slow compared to outline scheme because inline scheme always requires single step. We need single step to handle the original instruction, so it will be slow. How about outline scheme? Outline scheme is good because it works well with SMP or preemptive kernel. We always have breakpoint. We never recover the original by into original instruction. Okay, you can see here. We always have the breakpoint here. So we never miss it like in inline scheme. Right? And the other good thing is that it offers higher performance than inline scheme because we don't need single step. Outline scheme doesn't need single step, so it provides better performance. But it's bad because in the solution I propose here, we need cooperation from hijack virtual machine. That means we need to inject a kernel module inside. So you need some cooperation from that virtual machine that we want to hijack. So that is not easy to evade the virtual machine owner, and he can know that his virtual machine is hijacked. Okay, I have some performance benchmark here. Yeah, I run some micro benchmark. You can see that inline scheme is about twice slower than outline scheme. Okay, have some more demos. Actually, the hijack virtual machine technique I propose here can be used for good thing or bad thing. So first demo, we can use it for bad thing. In this demo, I inject some probe inside the virtual machine and I capture all the TTI system activities. So I can capture all the keystroke and output screen. So here's the demo. Okay, let's try to connect to SD again. Okay, now inside domain 0, I run one program. And this program inject 2 byte, only 2 byte inside SD. And let's see what happened. Okay, so watch this window, domain 0. Now we have a virtual camera, and this camera can capture all the activities inside the virtual machine. Oh, okay, so now see, I type. Can you see? Whenever I type, in domain 0, it captures the read and write event to the TTI subsystem. Now, because in domain 0, you can capture those activities, so we can replay it. Now I can replay it for you to see. Okay, so watch this window. Now, in domain 0, I type something. Can you see? Immediately, we capture the activities inside the virtual machine and replay it on domain 0 in this window. Like it? First of all, I try to edit something. And I move the cursor inside the virtual machine, you can see that it also moves in the camera. Yeah, yeah, of course. Okay, I can show it to you now. Okay, now sudo normally you don't see it. Okay, but because in the domain 0 we capture read and write event, so we can turn on the write event, turn on the read event. So I can show it to you now. So in the camera I turn on the write event. So okay, now can you see it? Password when it write down. Okay, it has gone. Okay, that is the second demo. So actually, I propose a demo for bad guys who can use it to monitor what happened inside the virtual machine. Because I suppose that he somehow compromised the domain 0 and he can monitor the activities inside the virtual machine. But actually, it can use for good thing as well. So imagine that you can use it to run a honeypot and you can monitor the activities of the attacker inside the virtual machine. So it's not necessary for bad guys. Okay, the second demo. In this demo, I have a Skype virtual IDS. So I monitor all the activities in the file system, and I capture the information related to the file system. And after that, you can see what happened, and you can verify against the policy to detect the illegal access. So here's how it works. Here's the scheme. So I probe the file system activities of the virtual machine, and I collect information. And after that, I verify against the policy. And if I see something not allowed in the policy, I fire the intrusion alarm. That means somebody try to break in to my virtual machine. So for the demo, here's a very simple policy. So in my policy, I define that you don't have a right to, you should not write anything into the critical directories. You should not change anything inside the critical directories. For example, you should not do anything in bin, /bin. You should not do anything in /sbin. You should not do anything in /etc. And you should not do anything inside /boot. Okay? That is a very simple policy. You should not change anything there. So here's a demo. Again, in domain 0, I run program which injects some probe inside the edge. And whatever happened to the file system inside the virtual machine will be detected. For example, you are inside the virtual machine now. Okay. Something wrong? Okay, something wrong. Sorry, I need to. Okay, I need to restart my virtual machine. Something wrong to it. Okay. Login. Okay, and inside domain 0, I run a program which injects some probe inside edge. Okay, now we have two windows. Here's domain 0, and we have an IDS here. Now let's try to I'm sorry, something wrong. Okay, but basically this demo can show you that whatever happened, for example, you create a directory, you remove directory, you create a file, you change mode, you change owner, you delete a file, you delete anything will be detected inside domain 0. And it verified against the policy. And for example, if you create something inside bin, it will detect. And because in the policy, it doesn't allow it, so we know that somebody tried to do something illegal. Oh, I'm sorry, that demo doesn't work. I don't know why. Maybe I need to restart my machine. Okay, so I have 5 minutes left. So, okay. I have a paper which I published in the last Unix Onion Technical Conference. And in that I describe the framework that do everything you just see. And the paper's name is ZenProbe. And ZenProbe is a framework, and it hands on the breakpoint, hands on the probe that we try to inject inside the virtual machine. So you can use it, and it do everything for you, does everything for you. So you only need to write the probe handler, and you just ask the framework ZenProbe to inject the breakpoint into the virtual machine for you. You don't need to do anything, just write the handler. So you can, the ZenProbe framework is released under GPL license here, and you can download from the internet. And in case you want to read the paper, it's also available here. So yeah, because I'm running out of time, so here's the conclusion. And you have some minute for question and answer. So in my talk, I show you that it's possible to hijack the virtual machine execution, and the owner might not know it. And we can do it without any cooperation from the virtual machine. That is, you can do it, first of all, using the inline scheme. Inline scheme might need some cooperation. And the technique work with own type operating system, be it Linux, BSD, Windows, or anything. And it work with own type OS configuration. First of all, with own type Linux configuration. And everything is done in user space. That means the probe handler is written in user space, so it's very easy to implement. So, as a customer, should we trust our rented virtual machine? Because I think virtual machine is popular in the many areas, first of all in ISP. So each customer can rent a virtual machine. And in that case, should we trust it? So the answer here is that no, because everything happen inside the virtual machine can be monitored. And actually the controls stay inside the people who own the physical machine, who own the domain 0 in Zen, not in, and the control doesn't stay in our hand. So here's a lesson learned. You should keep your hypervisor and your host virtual machine, which is domain 0 in Zen, as secure as you can. Because if you lose it, you lose everything. And you might even doesn't know it. So, yeah, my slide is pretty long, and in that I also discussed something about how to detect and how to anti-detect the hijack technique, but because I don't have enough time here, so feel free to look at the slide, and in case you have any question, contact me. Okay, here's a buffer again. If anybody can tell me how the demo that captures the SSH username password work, I can buy you a beer. Any question? Yes.
Did you do any analysis as to whether or not the same principles apply to other virtual machine technologies such as EMC's, VMware?
Yeah. Okay, I got that question many times. So actually, this technique doesn't only work with Zen. It works with other virtual machine as well. First of all, it works with KVM. It works with QEMU. It works with, I think it works with VirtualBox. I'm not sure, but I have a check, but I think it works. And it works with VMware version 6 as at least VMware Workstation version 6 it works. Yeah. Yes.
When you insert the breakpoint into the domain, into the virtual machine,
Yeah.
how do you know where you exactly have to insert the breakpoint? You have to know exactly.
So the question is where to insert, right?
Yeah.
Yeah, I have a slide about it. Probably you missed it.
You
Yeah, you have to know where to inject. You have to know exactly where to inject the breakpoint.
How do I know? Do I have to know which kernel version is running inside the virtual machine and which version of the
Okay.
page daemon is really running?
Okay. So where to inject breakpoint has like okay, this one. You can look at the kernel source code. For example, Linux, you have source code, right? You compile Linux with debugging information option. And from the kernel binary, which is this format, the WAI format, you can get a lot of information. For example, you know the virtual address correspond to this line of this file in kernel source code. And of course, you can always reverse the kernel binary and look at the assembly. And you can look at the kernel symbol file. This one is easy. Yes.
When you inject your breakpoint from the outside,
Yeah.
you don't only have to know where you have the virtual address of the symbol file and everything.
Yes.
You have to find out the physical address of your virtual machine to inject the breakpoint.
Yeah, actually, in the process that we inject breakpoint, we convert the virtual address into the physical address.
So how do you know where the pages are mapped?
Yeah, I have to pass the memory. That's a good question. I have to pass the raw memory to know where the page table. I can chase. I work the page table. But actually, that function is already available in the Zen API. Yeah. Any other question? Sorry for the last demo. It's broken. So, but I think you can get the idea. Thank you.